Welcome back everyone to 6034 Fall 2020 edition. This is recitation number 10 on boosting, more precisely adaptive boosting. And this is a recitation I'm excited for because it's one of my favorite topics in 6034, and in the outline I'll briefly explain why. Actually, I'll hold off on that. I'll explain why in the first section of today, AdaBoost plus supervised machine learning. So yes, for the fourth time in these recitation videos, I'll be talking about supervised machine learning, but yet in a different light than I was in the previous recitation and the previous two before that one. And after talking about the big picture, I'm going to go into the more intuitive sense of what AdaBoost is, adaptive boosting, and then we'll do an example in which I'll explain the algorithm of how it works, and then I'll give you a series of facts that the next time you have another AdaBoost problem you're trying to solve, it'll make it a lot easier having those in mind. They're generally very good rules of thumb to have in the back of your minds, and they also shed a little bit of clarity in what AdaBoost is as a mathematical object or a model. Okay, so AdaBoost and supervised machine learning. So what we've seen so far from supervised, I'm going to write ML. And this will be a hodgepodge of everything that you've seen so far. So far you've seen first Bayes nets. Then it was, if I'm not mistaken, KNNs and ID trees. Then neural networks. And then last week I talked about support vector machines. And these are all fine and dandy, and they all have their strengths and weaknesses as discussed in each of those recitation videos. I encourage you to look to go back and think about what their strengths and weaknesses may be. But let's say you have a bat of data, and you've taken the course, or you've seen all my recitation videos, so you know how each of those work, and you make a model for one of each of these models for this data, some hypothetical set of data, and none of them are able to perfectly classify all the data. So because they're not able to perfectly classify it, we're going to call these weak classifiers. And each of them is going to have some h sub some number associated to it. So it could be h sub 1 for Bayes nets, h sub 2 for KNNs, etc., etc. So you'll notice that because of their strengths and weaknesses, the points that they classify correctly versus incorrectly varies between them. So what if there were a way for you to, say, take the good points from one, or the good classifications from one, and the good classifications from another model? And that's precisely actually what adaptive boosting is. So a little bit more pictorially, this is what happens. You're making some sort of ensemble classifier. And Professor Winston used to say this was, if I'm remembering correctly, crowdsourcing, intelligence of the crowd, or intelligence of the masses, because this is essentially some sort of vote on the classification of each individual point. I'll explain this formula a little bit further as soon as I finish writing it. I find it really hard to talk and write at the same time often. Okay, so let's say we have a series of weak classifiers, lowercase h sub I, and we have not a perfect classifier, but a strong classifier, capital H. And capital H is, what it does is it sums all of these weak classifiers. Let me add the clarifications. So I should highlight this in red because this is actually where they all integrate. So it sums all the weak classifiers, and it multiplies them by a voting power. So the voting power is, you could say it's a weight, but because we're talking in the analogy of the wisdom of the masses, then where it's a voting, we are referring to the alpha sub I there as voting power. So it's an ensemble, and each of them has a say, and how much of a say in the classification of a particular point X, that is to be determined by the adaptive boosting algorithm, and we'll see how it is done here. And the primary way in which each of these classifiers gets picked and their voting power is attributed is with the error rate. And each classifier, each model that we've discussed so far in this series of videos, each classifier has an error rate. And I'm going to be using, as much as I can to be consistent, a red epsilon for this. So the error rate exists between 0 and 1. And you can imagine it's always the case because you would take the total number of points to be classified. You would take the total number of points that were classified incorrectly by a model, and you just divide it by the total number of points, and that'll give you the percentage, approximate percentage of how many points it classified incorrectly. That's what we're calling the error rate. And there are particular error rates that are useful versus particular error rates that are useless to us. And my hope is this will make it a little bit more intuitive. So let's say there's a classifier with an error rate of 0, classifier with an error rate, or some error rate 1/2, so half of the points were classified incorrectly, and then 1, so all the points were classified incorrectly. So if you classify exactly half of the points incorrectly, or you're close to getting half the points incorrectly, then a model with that error rate would have less voting power than, let's say, a model that has a very low error rate. So I would give a model closer to the 0 more voting power. So far so good. So one way of picking the classifiers is the minimum of epsilon, the minimum error rate. And if, let's say, a classifier has an error rate of 0, there's only need for that particular classifier because that classifier is able to classify all the points in just by itself correctly. But let's say a classifier has an error rate that gets close to 1. So we would actually give such a classifier more negative voting power. And I want to highlight the negative part. Whoops. And the reason I highlight the negative part is if a classifier gets absolutely all the points incorrectly classified, you could say, well, this classifier gets everything wrong, so whatever it says, I'll do the opposite. So that's actually a case where flipping, I'm about to give away a gold star idea that it's meant to be later in this recitation, so I'll stop there. But I'll just leave it at a lot of mistakes isn't necessarily bad, because you could just flip the sign or flip the prediction, and suddenly you get a very good classifier. And that case, so this is, if you're only looking at classifiers closer to 0, you're thinking of the minimum error rate. But if you're thinking in terms of 50% errors is bad, because if you flip it, you still get 50% errors, but 100% errors or 0% errors are good, then you're thinking of looking for something like this. So essentially, you're looking for epsilon, or the error rate, to be as far away from 1/2 as possible. never mind. The not minimum, because minimum would mean the error rate, the epsilon is 1/2, and that would give you a 0, and that would mean it's useless. So you would want to maximize this. Okay, so how to AdaBoost? So you have your classifier, you're looking for a strong classifier h of x, and you've assembled, you assemble it in a series of rounds. So for each round, roughly what you want to do is you pick the best weak classifier, and we're going to name that best weak classifier h star of x. And we're going to assign it a voting power. Let's say that's alpha star. And then finally, we're going to append h star of x to h of x. Seems simple enough. So now comes a question, what is the best classifier? H star of x. And as we briefly discussed earlier, h star of x makes either the fewest or the most mistakes. And it's adjusted to emphasize points that were previously misclassified. So maybe it's not that it commits the fewest number of mistakes, it's maybe that it misclassifies or it classifies correctly the points that we want to be correctly classified. And that's a notion that I'll get into during the example. Okay, and this is the gold star idea that I almost gave away earlier. And this is a really powerful idea, not just for adaptive boosting, but in general. And that is that mistakes are often more informative than correct predictions. Or maybe not often, I'm going to say sometimes. Which is to say, mistakes aren't necessarily bad. They can be very good and very useful. If they don't provide you with information, you could easily leverage them if they are too many in the case of a really bad classifier and turn it into a really good one by giving it some sort of negative voting power. Let me grab some water. I don't think this recitation will be as long as the previous ones, and yet I needed water for 15 minutes in. So let's go on to the example. So I'm different from previous recitations. I decided just to clip the example itself from the 2012 final, the quiz 4, not the 2012 final, the 2012 quiz 4 of 6034 of that year. And you're given the following data set. And it's just 5 points, A, B, C, D, and E. And you're told that your classifiers can only take this form. Either along the x dimension, x is less than something, or x is greater than something. So the first step when you see a problem like this is think, what are my classifiers? You have the constraints, but they're not necessarily formal yet. So these are going to be the classifiers. You have, I'm going to number them right from the start. H1 is going to be x less than or equal to 2. And then H2, x is less than or equal to 4. You may notice that I'm aiming for this, the coordinates that don't have any points on them, just because I don't want to have to deal with cases where a point is on the boundary, but then which classification do I give it if I'm doing less than or equal to or greater than or equal to. You'll notice I'm not very strict with the inequalities in this example. H3, x is less than or equal to 6. As I just alluded to, I'm not going to be particularly strict on these inequalities. So I'm going to say this is greater than or equal to 2 instead of strictly greater than 2. You can choose whether you have x less than 2 strictly and then x greater than or equal to 2, or vice versa. It doesn't change the result of this example. Typically, we won't be targeting very, very niche edge cases where this definition would matter very much. X greater than or equal to 4, and then H6, H greater than or equal to 6, as you may have guessed. So you have the weak classifiers defined, and I think a very, very useful the first step was defining what your classifiers are. The second step is determining what are the strengths and weaknesses of this crowd. And by crowd, I mean the ensemble of classifiers. What do they do correctly and what do they do incorrectly? And that's what I'll be detailing here. So here I'm going to write on the rightmost column the points that are incorrectly classified by these classifiers. So H1, I'm just going to briefly draw H1 over here, and then I'll erase it and go on with the classifications. H1 says it outputs a 1 for anything that's less than or equal to 2, and that's true for it correctly classifies A and D, but then B and E are incorrectly classified as minuses because they fall to the right side of this boundary, or they fall on the negative side of the boundary I just drew in red. Or let me draw it in black just in case it's hard to see. There. Which means B and E are misclassified. And because I have a weak classifier that is greater than or equal to 2, I can just flip. And if I flip it around, I see that C is misclassified because it would say that C is positive, and then A and D would be misclassified as well. So this would be A, C, and D. Let me quickly erase this. Let me draw a similar line along x equals 4 and think, okay, if it's pointing toward A and D, that means C is misclassified, B and E are misclassified as well. Then for x greater than or equal to 6, that would be here. C is the only point that is misclassified. And then for H5, where I'm flipping the inequality, it's just essentially the points that weren't misclassified by the first one. So in the case of let me clean up this before I confuse myself. In the case of x is less than or equal to 4, A and D were correctly classified. If I flip it around, they are going to be incorrectly classified, and everything else will be correctly classified. So A and D are the ones here. And then if C was the only misclassification in the case of x less than or equal to 6, then everything else is going to be misclassified if I flip it. A, B, D, and E. Okay, so now that you know that, you know what your weight classifiers are, you know the mistakes that your crowd makes, and I've already told you the rough algorithm, then you are perfectly prepared to solve this, and this is the end of recitation for today. Just kidding. I hope you could see from a mile away that I was kidding. No, we'll work through this example in more detail. So this is roughly how an adaptive boosting problem might look within 6034 on pen and paper. And the first question that you may have is, or the first natural question is, where do you even start? So let me label some of what is going on here, and then I'll proceed to tell you how to start this problem. So you have WA through E, and these are non-coincidentally A through E are the points, and the W's are the weights of each point. So this is actually perhaps one thing that might be striking to some of you is that we're associating points and weights. We're not associating, in this case, at this stage, we're not associating classifier with a weight yet. So we have points associated to weights, and here we have the error rate, or we'll be writing the error rate of each classifier, each hi of x. Okay, so now I'm going to tell you how to start. And the beginning is very, very easy. Another reason that this is one of my favorite topics within 6034 is it's also one of the most straightforward. So first up is to uniformly initialize all the weights. I really butchered my cursive there. Not that there was ever any moment where I didn't butcher my handwriting. So I'm going to initialize back on topic. I'm going to initialize each of my weights as 1 over n, where n is the total number of points. So each point is going to get the same weight. Let me just write it here relatively quickly. 1/5, 1/5, 1/5, and 1/5. It should be no surprise that all the points or all the weights sum up to 1. That's going to be the first sanity check. Did I initialize correctly? Well, did all the points have the same weight, and do they sum up to 1? After you've done this, then you can start calculating the error rate, because you know which classifiers misclassify which points. And let me give you the formula shortly. You calculate error rate epsilon for each hi. And the formula looks like the following. It is extremely straightforward. For each wrong point, j, you sum that weight. And that is it. Which means if I think back to how many points each each classifier misclassified, I feel free to go back to a couple minutes and check which points classified which, or write it on a separate piece of paper. Unfortunately, I don't have much board space here to write everything, to keep everything together. So I'm just going to say more or less how many points were misclassified by each classifier. You'll have to trust me on this one. So H1 misclassified 2 points. And if you remember from earlier here, so another note, I'm writing here less than and greater than, not less than or equal to as I was writing earlier. It doesn't really change the answer. I wasn't particularly strict in my inequalities because, again, I defined them such that no points were at the boundaries. I recommend you to be strict. This is a fairly informal, straightforward example. So where was I? Oh, x less than 2. If I flip it around, I'm going to misclassify the other points, which means x greater than 2 is going to be 3/5. X less than 4 misclassified 3 points, so 3/5, which means x greater than 4 misclassified 2 points. Let me double check those numbers. Yes, 2 points. It's not that I needed to verify. That's embarrassing. I didn't need to verify whether 2/5 plus 3/5 summed up to 1. I noticed some irregularities in my notes and I wanted to verify that I was on the right track. But we are on the right track. So this is how it will look. So you've calculated all the weights, or we initialized all the weights. We have all the error rates. What's next? And you've probably guessed it, we need to pick the best HI of x. In other words, the one that has the lowest. In this case, I'm going for, in this example, I think it bears mentioning that I'm going for minimum epsilon instead of maximum 1/2 minus epsilon. So I'm not going for this, I'm going for the minimum. So lowest epsilon I, or the error rate. This is going to be my H star, H sub I star from earlier. So I need to go ahead and pick. I'm just going to symbolize the pick by highlighting the best classifier, which is 1/5. And now I want to start tabulating everything. So for round 1, my best classifier was H3, which was x less than 6, and the error rate was 1/5. And if you remember, alpha is the voting power. I still have to calculate that, and unsurprisingly, that's the next step. Calculate voting power. Star for H star of x. And the formula for that is 1/2 the natural logarithm of 1 over the error rate over the error rate. So fairly straightforward so far. We won't ask you to evaluate the logarithm in real time. Just feel free to leave it in terms of the logarithm. And that's exactly what I'm going to do here. I'm not going to bother with the arithmetic. I'm just going to give you the answer. This one works out to be natural logarithm of 4. And the last step, which was, if you remember from earlier, was appended to the strong classifier capital H of x. I should add the vector everything. I drop the vector hat sometimes. It's not strictly necessary because it doesn't change. The answers mathematicians might might look away in agony as I drop it sometimes. It's going to be 1/2 natural logarithm of 4 times h3 of x. This is what appending the classifier is going, or how appending the classifier is going to look. Because I give the point or vector. I did it again. I give the point or vector to the classifier. This could be, the h3 could be a Bayesian net, for example. I hand it there, and it outputs some answer, and then I multiply it by the voting power that I found, and that's going to be the contribution of the Bayesian network's wisdom. So I've calculated the voting power. Now I need to ask, or we need to ask ourselves, are we finished? And that's the next logical question in this algorithm, as it usually is: when are we finished? And there's roughly 3 conditions, that one of which not 3 conditions. Any one of 3 conditions needs to be satisfied. The first one, if our strong classifier h of x is good enough, then we can stop. We're finished. And that good enough, for me it could be 0 error whatsoever, or maybe it could be 90% or 10% error, which means 90% correct. It'll classify 90% of all the points correctly. Whatever point we reach, whatever point or bar we set for h, that when we reach it we can stop naturally when we've done sufficient rounds. So maybe you don't reach the error rate that you wanted, but you also have a limit. You have limited time, so you say after 5 rounds, after 6 rounds, I don't want to do any more rounds, and I'll just cut my losses there. So that's also a valid stopping point. And the last one, which is much more significant, is when there are no good classifiers left. And what that means is, you're running your algorithm, you're running it through rounds and rounds and rounds, and you don't reach because you haven't reached neither the limit of rounds that you set for yourself, nor the error rate that you wanted. And suddenly the algorithm, you stop the algorithm and you see h star of x, whatever best classifier was picked that round, has an error rate of 1/2, which means your best classifier at that point is completely useless, because if you give it a positive voting power, at best it'll only classify half the points correctly, and the negative voting power is going to do the same thing, as we talked about in the beginning of the recitation. So half of the points correct and half incorrect is completely useless for our purposes in terms of binary classification. So if your best classifier is useless, then you're done as well. So if we're finished, obviously we stop. If no, we proceed to step 3. And this is perhaps the gold star of AdaBoost, or adaptive boosting, one of the gold stars of adaptive boosting. So we update the weights. Reminder that when I talk about weights, I'm talking about the points, and when I talk about voting power, I'm talking about the classifiers. So update the weights to emphasize points that were misclassified. And this is perhaps, yes, this is the gold star idea, but this is perhaps what, at least in my years TAing and taking 6034, what I've seen gives students the most trouble. This is the big concept to understand about adaptive boosting. So if I, in the case of this example, I classified all the points correctly except one of them, and let's say I have another classifier in the next round that classifies all the points correctly except that one point that the first one, it was H3, that H3 couldn't classify, and another one, then what use is it to me to basically ask this next classifier, how should I classify this point if it also classified it wrong? So when I look for a classifier, I am now looking for classifiers that are going to complement the weaknesses of what I already have. So I give more weight to points that I still haven't been able to classify correctly. That is this last point. So mistakes are more important than correct classifications. That the gold star idea that I gave at the beginning of the recitation, and you're seeing it again here. So there's this is the formula for calculating the new weights. It's going to be piecewise, and the top part is 1/2 1 minus the error rate epsilon times the old weight, and you're going to use this formula if the point xi was classified correctly. Then it's going to be 1/2 1 over epsilon times the old weight if, you guessed it, xi is classified incorrectly. As I mentioned earlier, I'm going to leave the arithmetic off the page and just write down the numbers. I encourage you to try this problem on your own once you've seen this recitation to make sure everything clicks and all the concepts make sense to you. So one thing that helps me often in this type of problem is I'm going to first highlight which points were classified correctly and which ones weren't. So these two were classified correctly, and D and E were classified correctly by H3. I only had problems with C, which was the annoying point in the middle. So this one is going to be in red. And I'll go ahead and give you these numbers. 1/8, 1/8, 1/2, 1/8, and 1/8. And you're already seeing this notion of misclassified points are more important in action, because the misclassified point has a much higher weight, 4 times the weight of the other points which were correctly classified. Okay, and now I'm flipping slides to keep myself on track. Now, in reality, nothing changed between the two, except perhaps this small typo. This should be 2/5. 2/5, and I believe that typo was in the, yeah, that's 2/5. My apologies for that. 2/5. I'll correct it I'll try to keep in mind to correct it in the next slides when it appears again. So now I'm gonna calculate the error rates for each of the classifiers. These are going to be 2/8. I recommend that you sit down and you work through this problem on your own again with which points, which classifiers, which weak classifiers misclassify which points, and then you just do the summation for those. So it's 2/8, 6/8, 4/8. I'm not simplifying the functions because it's going to make it easier to compare later. 6/8, 2/8, and then 4/8. And now I need to pick the best classifier, which is going to be, I am concerned with the minimum, not necessarily the absolute value of 1/2 minus the error rate. So I'm going to pick 2/8 here. And now I need to make the calculations from earlier. Let me just, which one did I pick? H1. Yeah, x less than 2. So this is H1, x is less than 2. The error rate was 2/8. Now that I've compared and contrasted, I'm just going to simplify it to 1/4. And while I'm at it, I'm going to calculate the voting power. It's going to be 1/2 the natural logarithm of 3. And now that I have the error rate, the last step is to append to the classifier, to the strong classifier, sorry. Natural logarithm of 3 times h1 of x. Am I done? So intuitively, if you have two classifiers, and in this case they don't have equal alphas, then the classifier with the larger alpha will always get the last say, or the final word. So in reality, the second classifier isn't really fixing the mistakes or covering for the weaknesses of the first classifier because of the imbalance in alphas. And even if they had the same alphas, if their mistakes overlap, there's still an issue. Or not even if they overlap. If they have the same alphas, how do you know which one to listen to? So we're not done yet. Little vector over the x, so that mathematicians don't think that 6034 is some mathless course. Okay, so here's a recap of what we were seeing earlier. I still have the best classifier highlighted. Now I need to calculate the new weights because as I explained just a few moments ago, I'm still not done because I only have two weak classifiers in the ensemble. I need a third one to get a third party's opinion, if you will, and then wrap it up. At least I'm only doing 3 rounds in this recitation, so I'll wrap it up there regardless of being done or not. So this is 1/8. I'm highlighting in green the points that were classified correctly and now points that were incorrectly classified. Now, this amounts to 1/12, 3/12, 4/12, 1/12, and 3/12. And one thing that I would like you to notice in what I've been doing so far is notice that the incorrectly classified point here ended up summing to 1/2 in the next step when I recalculated the weights, and the negatively classified points here, or incorrectly classified, ended up summing to 1/2 in the next step. And this is also true for these points. These correctly classified points ended up summing to 1/2, I believe. Oh, that's a typo, I think. Oh, no. Sorry. These 4 points, 1/8, 1/8, 1/8, 1/8, they all sum to 1/2. And these 3 points correctly classified, 1/12 plus 4/12, so that's 5/12, and then 6/12, they also sum to 1/2. That's a peculiarity that I'm going to talk about more at the tail end of the recitation in the AdaBoost facts section. But I wanted to bring it up to your attention because they can really speed up the computations as in you don't have to apply the formula at every single step. You can more or less develop not an intuition, but see mostly ahead of time what the weights are going to be, and that'll help you move through these problems much quicker. Okay. So I have that now. I just flipped the slide to keep myself on track. And Now I'm going to calculate the error rates. So this is going to be 1/2. And I'll say after I finish computing the error rates, 10/12, 4/12, 1/2, 2/12, and then 8/12. And I'm going to pick the best classifier. If I'm looking for absolute minimum, then it's going to be 2/12 down here. And that is H5. The other thing that I want to bring your attention to is, in the first round, my best classifier was H3 with an error rate of 1/5. In the second round, look at the error rate of H3. It was 1/2. And then my best classifier became 2/8. And from round 2 to round 3, look at the error rate of H1. It became 1/2. And then the next classifier was some other error rate. So that's another pattern that I want you to keep in mind, and then I'll clarify. I'll say it more explicitly in a detail end of this example. So I have my classifier H5. X is greater than 4. The error rate was 2/12. And then the voting power is going to end up being 1/2 the natural log of 5. I should say this is alpha star. Me thinking to myself. Whoops. There we go. H5 of X. And now the question is, are we done? Well, if you take out your list of points, you'll see that one classifier, the H1 or H3, sorry, is very good at classifying all the points except point C. And then if you go back to, let me briefly go back to the list of points that each of them misclassified. That was many, many slides ago. So the main classifier is H3. It misclassifies C. And then we have H1, which doesn't misclassify C, and H5, which also doesn't misclassify C. So the way the ensemble classifier, the way we've designed it in this example works, is H3 has the largest weight, and and we listen to it whenever it classifies any point, except for C. Because when we are about to classify point C, notice that H1 and H5 are in agreement about C and about no other point, which means that the weight of H5 and H1, or the voting power, not the weight, the voting power of H1 and H5 together is going to be greater than the voting power of H3, and they both jointly make up for the weakness of H3, of the weak classifier H3. And that is the beauty and the power of adaptive boosting. That's the reason it's one of my favorite topics in 6034. Aside from it being relatively straightforward, I think the greatest evidence of that is that we're at the tail end of recitation and it's not yet been an hour. Okay, so let's see. These are. I jumped ahead. I didn't jump ahead enough in the slides. So I'm back where I'm supposed to be. So for the tail end of recitation, I just want to cover a few facts about AdaBoosting, and I started hinting at them while we were working through the example to make you aware of these patterns. So these are generally true in AdaBoosting example, except in the small print that I wrote right underneath the title, except for weird degenerate cases, none of which will have you see or work on in 6034. So they are generally the case. The first one is that the sum of the weights of all the points is going to equal to 1. That is going to be true across all the rounds, and then a truth that follows right from that one is, or doesn't necessarily follow, but in line with that one, the sum of the weights of all the right points, I, is equal to the sum of the weights of all the wrong points, Wj, and they're both going to be equal to 1/2. And this is the trick that I was pointing out earlier, that this is that the weights, let me just write useful here, just in case, that the weights update proportionally from prior values. So that's I showed you how from one round to the other they still were summing to 1/2, the wrong points and the correct points. So that remains true across rounds. My throat is telling me that I need to drink some water before I go on to the third fact. Okay, so the third fact is that the best classifier, h of x, from the previous round will have an error rate of 1/2 in the next round. And that I also pointed out explicitly in the in the example where I said, okay, this was the best classifier. Notice the error rate in the next round, it's 1/2. I won't repeat it senselessly now that you've seen it. The fourth fact is that after the first round, the weights are going to be in the following range. So in this case, I do want to be strict about the inequalities. The weights are always going to be greater than 0 and less than or equal to 1/2. And they're never going to be 0. So the weights for a particular point, especially if it's a point that is correctly classified by all your candidate weak classifiers, is going to decrease and decrease and decrease, but it's never going to be 0. That's important to keep in mind. Mostly because, remember, the weight update equation, first you randomly, not randomly, you uniformly initialize all the weights of all the points to be the same value, 1 over the number of points, and then you keep multiplying to it. At no point you would multiply a 0 because you're multiplying W old by 1/2, and it was either 1 minus the error rate or 1 over the error rate. Where was I? Oh, yeah. It's now... It was... What was it? I know I said the reason I paused is I didn't really cite the weight update equation exactly the way it is. As in, you're multiplying the equation by some factor greater than 0, or less than 1 but greater than 0 at each weight update, and that's why you'll never get to 1. I mean, you never get to a weight of 0. You might get very close to 0. But I didn't, when I said you multiply it by 1/2 and something about the error rate, I know I didn't say it correctly. Just go refer to that equation earlier in the slides if you have any doubts. The last fact, at least in this slide, is more a repetition of, let me redo this line, is a repetition of the beginning of recitation as well, where we have a voting power of 0 if you have an error rate of 1/2, because it's useless to have a classifier with an error rate of 1/2 is useless, and an error rate of 1 means you can have a voting power of -infinity, because you've basically solved the problem with that one classifier. And then an alpha of infinity if you have an error rate of 0. Okay. So these are the 5 most basic facts. The next facts are going to be a little bit out of the scope of 6034. The coming facts start getting out of the scope of 6034, but I think they're really interesting and really cool. Some of them are useful to know, so I'll discuss them anyway. They involve a lot of text, so if you want to, my recommendation is stop the video and read through them, and then listen to me talking, or the other way around. I'll more or less read. As in, I know everyone knows how to read, so I don't expect you to listen to me reading to you the text that's on the screen. I just want to discuss them briefly and then move on to the next set of slides, or the next set of facts. And as promised, these are a little bit dense. Feel free to pause the video here, and I'll discuss these points in the next couple seconds. Okay, so assuming you've paused and read, or you're waiting for me to discuss and then read carefully, what number 6 is saying is a consequence of point number 2, where, was it point number 2? No, it's point number 3. That's an unfortunate typo. It's a point number 3. And the reason the weak classifier from the best classifier from the previous round won't be picked in the next one is that it's going to automatically have an error rate of 1/2 because of the way the points are reweighted. You know that the negative points, well, technically it's C2, 2 was correct there, and 3 is also correct there. It's going to have a weight or an error rate of 1/2 in the round after it was picked as the best. And remember that when we were talking about are we finished, the last point was if you have a best classifier that has an error rate of 1/2, as in when you pick the best classifier for that round and it has an error rate of 1/2, that means the best classifier is useless and you're done. So there should never be a case in which the best classifier from the previous round is again the best classifier in this round, because if it is, that means the algorithm is finished. The 7th point is, I briefly alluded to it when I had the strong classifier, capital H sub x, I had H3, and I had the other classifier, I'm blanking on I believe it was H1, and I asked, could we be done here? And the reality is no, because if the two alphas are equal, then you don't know which classifier to listen to when they disagree. And if one is greater than the other, then H3, for example, is always going to say the classification, or going to have the last word, because its voting power is greater than the second one. And this, I'm going to skip point 8 briefly and go to point 9, because this is in direct relation to point 9, or fact 9. The fact 9 says when you have two classifiers that disagree, right, you don't know which one to listen to if they have equal alphas, and if one has a greater alpha than the other one, then this one is always going to get a say. And that's why you need a third a third hand would have been convenient in this case. That's why you need a third classifier, because, and this is what happened in this example, classifier H3 classified everything correctly except for point C, and then the other two disagreed on everything except point C. So the sum of the voting power of the other two classifiers was greater than this one. And that is actually what I mean here by the triangle inequality. It's a little bit unfortunate that it's being cut out by the sidebar, but one way to solve it is you have three classifiers and they have disjoint errors, meaning that their errors are in such a way that their errors don't overlap, so they don't misclassify the same points. Notice that in our case, one classifier misclassified A and D and the other one was B and E. So their errors were completely non-overlapping, which means they disagreed and they were always overpowered by the first classifier because it had the greater voting power than any of the other two individuals. There are many. It gets hard to keep all the H's and subscripts in my mind and then keep in this information as well. So if three classifiers have disjoint errors, then having all their alphas be equal will allow you to make the perfect strong classifier that classifies all the points correctly. But they don't necessarily have to be equal. They can satisfy the triangle inequality. And I talked about it more extensively at the beginning of the semester, but the triangle inequality says very briefly that for any two sides of a triangle, the sum of any two sides will be greater than the third side. And this is true for any two sides and then the third side. So A plus B is greater than C, B plus C is greater than A, and C plus A is greater than B. So as long as the alphas are arranged that way and the errors of the weak classifiers are disjoint, then you can make a perfect classifier. But adaptive boosting is not guaranteed to pick them in that order or in any order. You might get adaptive boosting picking some fourth classifier before one of the others. That might work out to be that might work out to be the case. That's all I wanted to say about points or facts 7 and 9. Fact 8, I want to address very briefly. This is, maybe it's hard to read, the weight of an outlier point. So an outlier is a point in the data set that does not follow the trends of the rest of the data. And I've been discussing them in the previous recitations, where where a point, let's see, which recitation was it where I first started bringing the outlier? I think it was in k-nearest neighbors, where you had an area of points A and there was a B in the middle for some reason. And if you had one nearest neighbor, then it might choose B as a classification, even though you're in an area that was very clearly A's. And then there was a cloud of B's somewhere else on the screen or somewhere else on the space, and you would think, well, if your mysterious point is in that cloud, it would be a B. If it's in this cloud, it would be an A. So the B in a cloud of A's is an outlier in that case. In what would happen here in adaptive boosting, an outlier would probably be misclassified by a lot of classifiers. So in round 1, it's misclassified, say, and you re-update the weights it's misclassified along with a few other points, because an outlier is just an outlier. So in the next round, the outlier has a greater weight because it was misclassified along with other points, and then you pick another weak classifier, and that weak classifier is also unable to classify the outlier, and so now the outlier has an even greater weight in the following round. So that weight is going to keep increasing, and that's what I refer to by when I wrote in parentheses, the system gets anxious. When the more the system tries to classify this outlier and fails, the greater the weight of the outlier, until you get a weak classifier that is able to classify that outlier. Okay, as before, feel free to read, pause this video, read, and then I'll talk, or let me talk and then read. I just don't feel as though I'm reading to you, because I trust that you can read, and for me it's annoying when somebody reads to me when I'm trying to read. Okay, so talking about these, point 10 is not, it's basically a guarantee of some, it's not meant to be a guarantee, it's meant to be, if you have, let's say the classifiers that I picked, H3, 1, and 5, I believe, were the ones that I were using. Let's say they had some overlap in errors. What number 10 is saying is, just because they have some overlap in errors doesn't mean that I can't construct a perfect H from them. But it requires some tweaking and some careful analysis. It's for you to know that it's not impossible if there's some overlap in errors, but we wouldn't expect you to be able to come up with a solution in such a case. And the number 11 is a direct consequence of number 8 with the outlier here, because it'll take the adaptive boosting will prefer classifiers that have the lowest error rate first, and then if everything else has been correctly classified and you still have outliers, that's when the weight of the outliers is going to become critical. But otherwise, the problem is in classifiers that classify outliers well have overfit the data. And typically, classifiers that overfit the data will have a higher error rate. And so adaptive boosting will not consider them until they become absolutely necessary. There's the original adaptive boosting papers, or papers on adaptive boosting, can elaborate on this very well, and you can look this up on your own. I'll leave the discussion there because there's a lot of mathematical nuance into why adaptive boosting tends to not overfit. But this is also another very powerful quality of adaptive boosting, that it's resistant to some extent to overfitting. So for number 12, I decided to leave it in blank because I really like, this is something that I find really interesting, and I wanted to write it out myself. And let's make a graph here of the error rate of the strong classifier on the y-axis, and on the x-axis I'm going to write the number of rounds. So when you start, let's say that you have no classifiers, you have a really high error rate, and you're choosing classifiers through the rounds, and the error rate keeps going down. I take that back. This is what's happening. Maybe you introduce some bad classifier, and then you introduce a good one, and the error rate is up and down throughout the rounds. And this is the reason I confuse them. So you start out with a high error rate, and it keeps going down and down and down, and it will only keep decreasing as the number of rounds goes further. But that's not the only thing, that the error rate is always going to be decreasing, because obviously you're giving weight to what you're still misclassifying, and so as time progresses you're going to misclassify fewer points. What is really interesting, and I think I did a poor job of this line, that's maybe a little bit clearer. Unfortunately, it's not. My artistry skills are betraying me here. This is the surprising fact about AdaBoosting to me. The total error is upper bounded by an exponential decay. function. So this is the exponential decay function. I accidentally drew it mistakenly instead of the error rate first. But the error rate may shift up and down, but it's always going to be upper bounded by, or that the exponential decay function is always going to be the ceiling in that progression of the error rate up and down throughout the rounds. And that's I think is extremely powerful and extremely cool about adaptive boosting. And now I'll move on to the last fact. I promise this is the last one. I think I'm on the money for finishing this recitation within reasonable time. Let's remember when I was making the distinction between choosing the minimum error rate or the maximum of 1 minus the absolute, or the absolute value of 1 half minus the error rate. So let's say you're doing the classic, and by classic I mean minimum error rate is best. So if let's say you're doing that. If h1 of x's, or the errors of h1 of x are a strict, I think writing them mathematically is going to be a little bit easier. The errors of h1 of x are a strict superset of h2 of x, or the errors of h2 of x. Let me write this a little bit more clearly. Let's say this is the set of errors committed by h1 of x. And let's say that's a strict superset of the errors committed by h2 of x. Then h1 of x will never get picked. If you think about it, so if you're looking for the minimum error rate, then h2 of x, or sorry, in this case, in this setup, h1 of x commits all the same mistakes of h2 of x, the weak classifier h2, and a few more. That's what I mean by a strict superset. So h2 always commits fewer mistakes than h1, which means h2 will always be preferred if you're looking for minimum error rate. Because, and the other reason to look at it is h2, let's say h2 is picked before h1 because minimum error rate, that means the error rate of h2 the next round is going to be 1/2, and the error rate of h1 is going to be 1/2 because it misclassifies the points of h2 1/2 plus something else. And so some other classifier is going to satisfy the minimum, or it's going to be h2 again, and then the algorithm's going to shut down because the best classifier has an error rate of 1/2. But let's say you're not following the classic minimum error rate is best. Let's say you're following the rule max 1/2 minus error rate, meaning you want the error rate to be as far away from 1/2 as possible. Let's see, the maximum 1/2 minus error rate is best. That's what I'm missing. So if, again, this is the set of errors committed by h1 of x, is a strict superset of the errors committed by h2 of x, and that's a strict superset of the errors committed by h3 of x, then the error rate of H1 is going to be greater than the error rate of H2, and it's going to be greater than the error rate of H3, and or because of this, and you may intuitively just look at it and say, okay, H3 commits a set of errors, H2 makes those mistakes and a few more, and H1 makes those mistakes and a few more on top. So that's why the error rates are in that order. Then H2 of X would never be picked. And intuitively, to think about it, H3 commits very few errors, so if you're looking for the minimum error rate or the error rate furthest away from 1/2, so either a lot of errors or no errors at all, then out of the three, H3 would be the one to pick in terms of fewest errors. But if you're looking for maximum amount of errors, you would pick H1. H2 is in that middle ground where it's not really, there's a better choice for there's a better choice than H2 in either of the two scenarios, intuitively speaking, and that's why H2 would never be picked by adaptive boosting. That's all I have to cover for today regarding adaptive boosting. I hope that in seeing how straightforward it is and seeing how so many important concepts just come together and how it relies on different architectures and the strengths and weaknesses of different models that we've seen in 034 throughout these recitations and in the course, that you see why this is perhaps my favorite topic out of this course. And I hope that even if it isn't your favorite topic, that you can at least get excited about it and about some of these facts and the power that such a model has. And I encourage you again to try this example on your own time. Perhaps print out the slides that I make available in the description, or just take screenshots of the slides and go through the mathematics of these points. Perhaps now that you know the facts about adaptive boosting, particularly the first 5, perhaps use those in calculating the weights and the error rates of the example that I worked through. But just on your own time, to make sure that you know all the facts and that you know where the different numbers go, because I know that there is a high potential for missing some basic arithmetic, or simplifying a function wrong, those easy mistakes, or perhaps a more conceptual mistake might arise. That's all for today. Hope you liked it, and I'll see you on the next one.